something. Oh, okay. Okay. Good morning, everyone. So this, after Professor Soper's introduction, some general ideas about the workshop and microfluidics, we're moving to this part where we'll be discussing different fabrication techniques and different ways to use the microfluidics in more detail. And what I'm going to talk about in the morning today is micromachining using high precision micromilling. This is one specific type of the techniques that are called direct write techniques. And there are very similarities between many different direct write techniques. And so you can use actually this talk as in a sense, to get the idea how other methods in this category would work. So there are different ways. Any book you will take on microfabrication or different review articles, you will learn about different ways to categorize the microfabrication techniques. One of them is to talk about the direct microstructuring. And here we can have two major categories. One is the mask-based global patterning technique, where we have some kind of mask and we have the patterning medium. And this patterning medium may be radiation, liquid or gas etchants. We can do additive process where we can selectively deposit metals or the electrics. And processes that fall into this category are UV or X-ray lithography, wet etching, deep reactive ion etching, evaporating techniques. The other category in direct microstructuring techniques are so-called maskless, where we use some kind of tool to shape the substrate. And this can be CNC micromilling, laser writing, where the tool is beam of laser. We can do ion beam lithography. Again, the tomb will be beam of ions that can pattern the plastic down to nanometer dimensions, e-beam lithography. And as we're 3D printing, and here is this filament-based techniques where you extrude, where your tool will be hot extruder to extrude the plastic that you can, in additive process, build microstructures or macrostructures in this sense, or you can have mirror-based projection type, UV light, 3D patterning techniques. So what is, click it, what is micromilling in general first? So how milling works is it uses the tool, which is called micromilling or milling bit or end mill, depending on person who calls it. And you can see here a process, how the process works. There is a CNC control, which means computer numerical control machine, where controls X and Y axis to move your substrate. And then there is a spindle that rotates the tool really quickly. And as you can see, let's just play it quickly again. The tool directly follows the path that's set up in the software, and you can form different microchannels or different type of structures. And just as an example, this is the desktop CNC milling machine, a relatively low cost unit, and two examples of milling bits were very common. End mill for micromilling uses 1/8 inch chunks, so you can mount it actually here in the spindle. But then tools themselves, the cutting edges can be 1/8 inch side or down to 50 or even 25 micrometers. So how do we go about the wrong one? Okay, how do we go about the making device when we have the idea? And this follows, as I said, this you could use this whole flow chart for pretty much any type of direct write tool-based techniques. You're just changing the machine that makes your structures, right? So we're starting with the idea, then we make a design in CAD, some kind of CAD software, right? Then we have to post-process it using CAM software, which means we're telling the machine how to treat whatever, how to recognize the structures that we drew in CAD. So how to make it, what type of, in milling, for example, what type of bit use, how deep to cut, what are the speeds and feeds of the tooling. Then we set up the milling machine, we put our substrate load it into the machine, and we perform CNC milling, right? And this process we can repeat many times, and every time we run it, these two steps, we pretty much can make another device, right? And once we have milled part, we can assemble it, and like in this colorful example, fill the channels and use them for our application. When we're talking about the high precision milling, it's a little bit different from this little benchtop machine that you've seen in this introductory slide. Now we're talking about using tools that go down to 25 micrometer in size, and you really need SCM to see them well and see their characteristics. There's this comparison to human hair, and as Professor Sopra mentioned earlier, there's nothing micro about the tooling used to make the microstructures with those tiny tools. This is the current Evo micromilling machine that's here on KU campus in Physics Machine Shop. It has, you can read at your free time at different specs for this machine, but you can see it's extremely accurate, extremely reproducible, can really quickly spin those tiny tools, and it can work for many different materials, for metals, ceramics, plastics. It has automatic tool changer shown here that really helps you to pre-program entire manufacturing procedure. There are two main applications for direct write using milling, and you've seen this in this first colorful example of directly machining your structures into the piece of, for example, plastic. Then we can just put cover plate and our device is ready. What we use it more often is machining of molding masters, where we first machine the metal structure that then which one we can use in the replication process to make reverse structures of our mold masters into, for example, plastic. And you can see here two examples of the simple cross structure. These are the brass structures that then were transferred, forming the microchannels in PMMA. What things do we need to consider when we choose micromilling as our fabrication technique? And in this sense, pretty much of any tool-based technique. First thing is that you're using tools that have physical dimensions and physical characteristics, and you have to be aware of this. So for example, if you want to use cut your channels directly into a piece of material, the smallest channel which you can make obviously will be the smallest size of the tool you're using, right? You cannot make it any smaller. However, tools have certain aspect ratio, which is the ratio between height of the tool to the width, which is typically between 3 to 5, which means you cannot make this channel that you're making any deeper than you're cutting part of the tool, right? So let's say if you decide to use 25 micrometer bit and your aspect ratio is 4, for the bit, you cannot go deeper than 100 microns, right? And in this case, because we can cut as close as we want, just depending on the material characteristics, we can make structures that are limited, so cuts that are limited by the size of the tool, but they can be really close to each other, right? It's a little bit different when we're talking about the replication, because now our structures can be really tiny because we're cutting right in between them, right? However, the spacing between structures is limited by the tool we're using. Another thing to consider if we're doing this, especially for the molding tools, is that the tool has some radius, right? Some size. So when you're making inner corners, I mean, there is no way to make really right straight corner. It will have to be some radius. And depending on the radius of the milling bit, this radius can be noticeable, like in this cross, or barely noticeable, like this one, right? So this all will dictate, I mean, also your application will dictate what you really need to, and whether you can use this milling technique for your application. The third thing to consider is there is a physical roughness to the cutting edge of the milling bit. And this roughness transfers to the sidewalls of your devices, right? And although the roughness is not, I mean, depending on the application, can be a lot or nothing. It's the peak to peak at 500 nanometers if we measure it up down. Again, something to have in mind when you're producing parts for your specific application. A few examples. You can see different, these are all brass structures, different shapes of channels. You can make high aspect ratio structures. You can see that those tiny walls are only 20 micrometers wide and 400 micrometer in height. And the reason is that these are raised structure on the surface. So we can use bigger tool, and this material is what's left. So the size of this material is not really limited by tool size, right? The other nice thing about micromilling is that in single step, machining step, you can make different height of the devices on the same substrate. And as you can see here, we have set of micro channels of 2 different heights. We can make structures that are not necessarily just vertical, as you would see with lithography technique in most cases. You can actually shape them. And this is example from Professor Soper lab, where we're using this array detection chip with the embedded waveguide and light coupling prism. So you see that this coupling prism required producing angle structures. It's very useful tool when you're thinking about connecting different chips together and making different interconnects, or actually connecting the outside pumps and valves to the chip. You can make different type of inlet ports that can be easily replicated in thermoplastics. We can also make stencils. So we can make actually our molded piece from, so we can start with the brass tool, make the plastic replica, and use this one for casting of PDMS. And I'll show a few more examples later during the PDMS casting part. And this is one of the examples that I really, like. It really shows where micromilling can be extremely useful as a rapid prototyping technique. So this is the project where we're using this 96, so microfluidic chip in the format of standard 96 well plate. You can see each piece here is basically tiny SPE, solid phase extraction microreactor with the inlet. So we have 96 of those connected with microfluidic network. And of course, before you invest time and money in making nickel electroplated design in Liga, you would like to test if your fluidics work, if your idea of addressing all those beds through only 2 ports, literally, and inlets to each bed will work. So micromilling proved really useful. We're able to make the brass tool whole from the design to first embossed chip took about 5 days. As far as the milling process, to mill this plate was probably about 2.5 days, but 2 days were really about milling those tiny holes that will end up post on the molded chip. This shows you one of the limitations. So it shows a good example of how great it is for prototyping. It's quick, but at the same time, it shows you a limitation. If you have to make really tiny structures repeatedly and lots of them, it can take a lot of time just to make it, versus when you use lithography, this global mask type techniques, it's pretty much one exposure to make all of them. And here's the example of the assembled chip compared to the tighter plate. So in summary, attributes of high precision micromilling: it's fast, inexpensive, once you have the proper equipment. It's good for rapid prototyping in either direct, right, or via hot embossing. You can get aspect ratios higher than 10, 2:4 for direct, right, limited by the tool you use. You can really produce highly vertical walls, pretty much any shape or size of the substrate. As long as it fits in your machine, you can structure it. You can do 2.5D or 3D components, which will give you a chance to make multi-level structures, sloped walls. And you can make in the same program and pretty much the same machine run, you can do both micro and macro features simultaneously. Limitations: feature dimensions higher than 5 micrometers. Definitely, that's probably already pushing for milling. Inner feature spacing, as I said, limited by tool, about 25 micrometers, rounded inner corners, and the wall roughness. Thank you for your attention. Do you have any questions? Yes.
Wall roughness, whenever you actually fill a mold, how much does that transfer to the final product?
Let me see if it's on this graph. We have it in this paper. There's reference. It's microfluidic, nanofluidics. Pretty much, it will really depend. If it's too rough, it will be difficult to mold in the first place, right? I would say if you have really good molding and it replicates really well, you will see all this roughness on the plastic. However, you can undermold it, which means by controlling your molding conditions or hot embossing condition, you can reduce amount of this roughness. However, I would say you will see some form of it there. Yes. So this, this was the micromilling. Yeah, and holes were 100 micrometer in this case. This is UV Liga that you will hear. This is a lithography-based technique. So we can make the diameter of, well, these were actually diamond-sized posts, right? So the side of the post is 20 micrometers or down to 10 micrometers. But this is lithography-based. So it's just to really give you idea that you can relatively quickly, you have the idea, and if you have equipment and resources, you can quickly, okay, let's make the mold, let's test how the fluidics, does it work? Can we pump it and push it at the same time uniformly, right? We have it, okay, let's invest time and money, because 5 weeks, it's also in a sense, it often takes longer, right? With iterations that you have to do. That's for somebody who really knows what they're doing and how they're doing. And it's really, it's not as simple as having a design, post-process it, give it to the machinist, he preps the, let's say, brass, mills it, ready to use. This one is really labor-intensive process, right? And time-consuming. Yes. So it takes, yeah. And the problem is if it doesn't work, you repeat it. So you're adding another 3 weeks, right? So that's the But I mean, you cannot, there is no way micromilling can get any close in as small size as you can do by lithography, right? So there are some benefits. Okay, thank you. And I don't have, do I have time? Yeah, let's move.